Welcome to the deep dive. Today we're looking at something really cool, binary stars. Not just, single stars out there alone, but pairs. Actual pairs dancing through space. It's pretty mind-bending when you think about it. But how do we even spot these pairs? And maybe more importantly, what are they telling us about, well, everything else out there?
That's a great place to start because finding them isn't always easy. Astronomers have developed a few different ways. You've got your visual binaries. You can actually see both stars with a good telescope. They're far enough apart. Simple enough.
Okay.
Then there are eclipsing ones. From where we are, one star passes in front of the other, so the light dims periodically. We see that dip.
Like a little eclipse.
Exactly. And astrometric binaries. These are trickier. You see a star doing a tiny wobble against the background stars. That wobble means it's orbiting something we maybe can't even see directly.
Ah, okay, so it's being tugged.
Precisely. And then the ones we're focusing on today, spectroscopic binaries. Now, these systems are usually really close together, too close to see two separate stars. We find them using light, specifically the spectrum of the light. There's this thing called the Doppler shift.
Like the sound of an ambulance siren changing pitch.
Exactly like that, but with light waves. As the stars orbit, they move towards us, then away from us. That motion stretches or squashes the light waves, shifting the lines we see in their spectrum. If we see the lines from just one star shifting back and forth, we call it an SB1 single lined. If we can see lines from both stars doing this dance, it's an SB2, double lined.
Right, so we're diving deep into those spectroscopic binaries, the SB1s and SB2s found by that Doppler shift, and this is where something like the Gaia mission comes in, yeah.
Oh, absolutely. Gaia is a game changer.
Because it measures positions so incredibly well.
Yes, astrometry is amazing. But it also measures brightness, the photometry, and those radial velocities, how fast stars are moving towards or away from us. That velocity part is crucial for spectroscopic binaries.
So it's got all the tools needed.
It really does. It can find and measure all these types of binaries, visual, astrometric, eclipsing, and spectroscopic, in just enormous numbers.
Okay, so our mission today then is to unpack what Gaia is telling us about these spectroscopic systems, and specifically I hear there's a surprising story about how their orbits get shaped.
Yeah, it's the core of it, yes. It's quite a twist on what we thought we knew.
Okay, let's unpack this. When you say enormous numbers from Gaia, what are we actually talking about here? Put it in perspective for us.
Well, the numbers are, frankly, a bit staggering. There's a key paper by Uranu and colleagues from 2023 looking at Gaia's Data Release 3. They identified over 181,000 of those single-line spectroscopic binaries, the SB1s, plus about 5,000 double-lined ones, the SB2s.
Wow, 181,000 compared to what? What did we have before?
So think about older catalogs. The big one, called SB9, had maybe around 4,000 orbits in total. More recently, a survey like APOG found perhaps 1,000 new orbits. Gaia's Hall is, well, nearly 2 orders of magnitude bigger. It's just a completely different scale, a huge leap forward.
Okay, that is a massive increase. So what's the real significance of having, not just more data, but this high quality data on such a scale? What does it let scientists actually do?
It's transformative. I mean, with these kinds of numbers and the quality Gaia provides, we can finally dig into the statistics of short-period binaries in real detail. We can ask, how common are binaries depending on the main star's mass?
No.
What do the mass ratios look like? Are the companions usually much smaller or similar in size? And really importantly, what's the link between how long it takes them to orbit, the period, and how circular or stretched out that orbit is, the eccentricity?
What the shape of the orbit?
Exactly. Getting solid answer to those questions is fundamental. It tells us about how these pairs form in the first place and how they change, how they evolve over millions or billions of years.
Okay, but with, over 180,000 potential systems, I imagine you have to be careful. How do you make sure the data is reliable? How is it validated?
That's a crucial step, absolutely. And that's where another study by Bashi and colleagues in 2022 comes in. They took that huge Gaia list, which already had preliminary orbital details, the Keplerian elements.
That's like the orbits recipe, period, shape, tilt.
Yeah, basically. But Gaia didn't have detailed velocity measurements for every single observation of every star. So Bashi's team cross-matched the Gaia candidates with other big ground-based surveys that do have lots of radial velocity data. They used Lamost, that gave them over 17,000 stars to check, and Gaia, which added another 6,000 or so.
So comparing different measurements of the same stars.
Exactly. It helped weed out any systems where the orbit calculation might have been shaky, or maybe wasn't even a binary at all. This whole process gave them a clean sample, still huge, mind you, 91,740 high-quality SB1 orbits, all with reliable orbital elements.
91,000 confirmed orbits. That's still an incredible data set. So what did they see in that clean sample? Did anything jump out immediately?
Yes, a couple of key things emerged from that Boschy 2022 work. First, they noticed there seemed to be fewer short-period binaries where the main star was low mass. A paucity, they called it.
Fewer than expected.
Yeah, though they thought that might just be because fainter, low-mass stars are harder to observe well and observational bias, potentially.
Okay. What else?
The other thing, and this is really the main thread for us today, was a significant group of binaries where the stars were on the main sequence.
Like our sun, in the stable part of their life.
Exactly. And these main sequence binaries had orbits that were very, very circular, especially the ones with short periods. This wasn't just a few, it was a clear pattern. And they took this as strong evidence that some kind of circularization process must be happening. Something is taking orbits that might have started out more elongated and making them round.
Right, so orbits aren't necessarily born circular, they become circular. Why is focusing on that specific process, orbit circularization, so important? It sounds kind of technical, but you're saying it has bigger implications.
Oh, definitely. If you zoom out, multiple star systems are incredibly common. We think maybe 35%, over a third, of Sun-like stars have companions. And for the really massive, hot O-type stars, it could be as high as 70%.
Wow, so being single might be the exception for some stars.
It could be, yeah. And having a companion, especially a close one, dramatically changes how both stars live and die. It's not a quiet neighbor situation. Their interactions can lead to all sorts of exotic outcomes. Stars spinning incredibly fast, systems that blast out X-rays, exploding stars called novae, even stars with really weird chemical compositions like barium stars or carbon-enhanced stars.
So the companion directly causes these
It
things.
drives them, yes. And these processes, they're major ways that heavy elements, things heavier than hydrogen and helium, get created and spread throughout the galaxy. Understanding how binary orbits evolve, including circularization, is actually key to understanding the chemical enrichment of the entire Milky Way. It's a big deal.
Okay, I see the connection now. And the physics behind the circularization. You mentioned tidal friction. Is that like ocean tides?
It's the same fundamental forced gravity, just on a stellar scale. Each star's gravity raises tides, bulges, on the other star. These are called equilibrium tides, but it gets more complex. The gravity can also excite actual waves or oscillations inside the star, kind of ringing it like a bell. Those are dynamical tides. Okay, so bulges and internal ringing. Yep. And both processes, equilibrium and dynamical tides, effectively drag on the orbit. They sap orbital energy. Over long time scales, this makes the stars spiral closer together slightly, so the orbital period decreases. It also dampens any eccentricity, making the orbit more circular. And it tends to push the star's rotation speeds to match their orbital period, something called spin-orbit synchronization.
So the system kind of settles down into a more stable, circular, synchronized
That's
state.
the tendency, yes,
Yeah.
driven by these tidal forces.
Now, you said this Gaia stuff was a twist, but the basic idea of tidal circularization, that wasn't completely new, was it? I think you mentioned some older studies.
That's right. People have seen evidence for this for decades. Studies back in the 80s by Mayer and Vermillion and Matthew and Mazza, they looked at star clusters. They found a clear pattern. Binaries with short orbital periods, say less than a week or two, tended to have perfectly circular orbits, zero eccentricity. But binaries with longer periods could have all sorts of eccentricities, quite stretched out orbits.
They called this a cutoff period, right? Below the cutoff, circular. Above it, eccentric.
Exactly. And the thinking was pretty straightforward. Tides are much, much stronger when stars are closer together. So in short period systems, tides have had enough time to circularize the orbit. In longer period systems, the stars are too far apart for tides to be effective over the star's lifetime.
And people use this cutoff period.
Right. Well, in star clusters, where you can estimate the age of the stars, they saw that the cutoff periods seemed to be longer in older clusters. So they used it as a kind of clock, an observational measure of how efficient tides are. And the widespread assumption, the inference for decades, was that this circularization process happens mostly while the stars are on the main sequence, during that long, stable hydrogen burning phase. That seemed to fit the observations reasonably well.
Okay, so that was the established picture. Tides work slowly during the main sequence, circularizing the closest pairs over time. But now, Gaia enters the picture.
Right, and this huge, clean sample of spectroscopic binaries from Gaia DR3, analyzed again by Bashi and colleagues in 2023, provided a completely fresh look.
And they focused on main sequence stars again.
Yes, they selected about 17,000 main sequence systems from that validated sample of 91,000. They specifically looked at stars classified as A, F, and G types.
Can you remind us quickly what AFG means?
Sure, it's basically a temperature sequence. G-type stars are like our sun, around 5,000, 6,000 Kelvin. F-type are a bit hotter and slightly more massive, maybe 6,000, 7,500 Kelvin. A-type are hotter and more massive still, up to about 10,000 Kelvin. They picked these types because they're common and well understood.
Okay, so they looked at the orbits of these 17,000 AFG main sequence binaries from Gaia. And what did they find? This is the twist.
This is the big twist. What they found was really surprising, that circularization cutoff period. It doesn't seem to depend on the age of the stars like people thought.
No age dependence.
Not significantly, no. Instead, they found it depends very clearly on the star's temperature and therefore its mass. They saw the cutoff period decrease linearly as the stars got hotter. It went from about 6.5 days for the cooler G stars down to just 2.5 days for the hotter AF boundary stars.
Whoa. So hotter stars only circularize if they're really close. Cooler stars can circularize even if they're a bit further apart, but age doesn't matter.
That's what the Gaia data strongly suggests. And this finding, especially for the F and G stars like our sun, just doesn't fit the standard theory if you assume circularization happens only during the main sequence. The tides during that phase just aren't strong enough or don't work fast enough to explain this temperature dependence without an age dependence.
So the old assumption is shaky now. If circularization isn't happening primarily on the main sequence, what's the alternative? When is it happening?
Well, the explanation that Bashi and colleagues favor, the one that fits this new data best, is that most of the circularization actually happened much earlier during the pre-main sequence phase.
Before the stars even settle down to become normal stars.
Exactly. When stars are first forming, they are much larger, puffier, still contracting towards the main sequence. They have huge convective zones.
Bigger targets for tides.
Much bigger, yes. And being larger means the tidal forces between the binary pair would have been vastly stronger. Circularization could happen much, much faster than, perhaps in only a few million years, compared to billions on the main sequence.
So the orbits got set into their circular or eccentric shapes really early on.
That's the idea. The eccentricity distribution we see now was essentially locked in during that very early pre-main sequence stage. And what's fascinating is this isn't a brand new idea out of nowhere. Mayer and Vermillion actually hinted at this possibility back in their 1984 paper. Others like Zahn and Boucher explored it theoretically too, but they lacked the huge, precise data set like Gaia's to really prove it.
So Gaia's data gives that old idea new life, strong evidence. What about the earlier findings that the cutoff period did seem to depend on cluster age?
Bashi et al. Suggests that weak age dependence seen before might have been a bit misleading, maybe just a consequence of the specific, often different temperature ranges of stars sampled in those older cluster studies. The primary driver, they argue, really seems to be temperature set during the pre-main sequence.
Okay, that makes sense. Was there any other work that supported this idea of early circularization?
Yes, actually. Another recent study by Moreau and colleagues in 2023 looked specifically at tidal effects in 8 different open star clusters. Their analysis also concluded that tides on the main sequence are pretty inefficient as circularizing orbits. It adds more weight, more circumstantial support to this idea that the heavy lifting of circularization happens really early on before the main sequence even begins.
So let's pull this together. The picture seems to be shifting quite dramatically, thanks to Gaia. The conclusion from Bashi et al. Is that orbits get circularized mostly in that very early pre-main sequence phase. You said this is potentially far-reaching. This isn't just some minor detail for binary star experts.
Not at all, no.
Yeah.
Getting the timing and efficiency of tidal circularization right is incredibly important. It affects how we model the evolution of all close binary systems. And that, in turn, impacts our understanding of so many other things. Think about close triple star systems, how they stay stable. Think about cataclysmic variables, those interacting binaries that cause novae. Or X-ray binaries, which involve neutron stars or black holes feeding off a companion.
And even bigger things.
Yes, even the mergers of black holes or neutron stars that produce gravitational waves. The evolution of the binary that formed those objects is shaped by tides. If the circularization happens early, it changes the starting conditions for their later evolution and eventual merger.
And what about planets? Does this affect exoplanets?
Hugely. especially those hot Jupiters, giant planets orbiting incredibly close to their stars, much closer than Mercury is to our sun. How did they get there? One leading theory involves tidal interactions with the star. Understanding when the stars orbit in a binary system circularize tells us about the environment and the tidal forces that might have been acting on any forming or migrating planets very early in the system's history. If the stellar orbit circularized pre-main sequence, that sets the stage for what could happen to close-in planets later on.
Wow. So it connects all the way from the details of stellar physics to potentially how planetary systems, maybe even habitable ones, form and evolve.
It really does ripple outwards.
So think about that. A subtle gravitational dance between two stars, maybe billions of years ago before they even fully formed, could be setting the stage for everything from brilliant stellar explosions to the fate of planets orbiting them today. It makes you wonder, what other really early, almost invisible processes might be shaping the cosmos we observe now?